Alrighty guys, so today we're going to be doing section 4.4, and this is, in my opinion, this is the weirdest one because we're going to graph the other functions that aren't sine or cosine. So tangent, cotangent, secant, and cosecant. So anyway, we're going to start with just the boxes for tangent and cotangent. So first I'm going to kind of graph the shape for them. When you're dealing with tangent, excuse me, tangent starts off here, goes up here, there's a vertical asymptote right in the middle. So already it's weirder than the others. And then here and here. So when you graph it, what you're going to do is draw kind of like a half parabola going all the way up. I guess I won't make it interrupt that. Half parabola going up, and then like a half parabola going down on the other side. And so that's tangent. It's kind of weird. Um, However, everything else stays the same, meaning that the k is right here. This is k. And all you do is it's the amplitude. I just put an h for amplitude plus k, negative the amplitude. I keep on doing h. Let me zoom in. There we go. Negative the amplitude plus k. So just like it was for sine and cosine. And here, again, what you do is you have an inside of your tangent. And you get the inside of the tangent and you solve it. And when you do, that gives you the bounds for the edges. And like before, a quarter is the same formula as before, just 1/4 times the period. One thing to notice is that for tangent and cotangent, this goes from 0 to pi, not 2 pi. Right? So that's a big mistake that people tend to make. All right, so that's for that one. That little circle up there is bugging me. A little OCD up here. All right, anyway, same thing here. We're going to the inside for cotangent. Goes between 0 and pi. That gives you the two edges. And then again, a quarter is just going to be 1/4 times the period. Same thing as before. K, absolute value of A plus K, absolute value of the amplitude plus K. Now, the way cotangent looks like in comparison to tangent is cotangent looks like that, where we have vertical asymptotes on the edges. Okay? And, wow, I did start it that way too close. So, we still have that same half parabola shape, but then the parabola turns upside down and it looks like that. So that's cotangent. Again, it just takes getting used to, but these are the two weird ones of the group, meaning that they're not related. Like their graph doesn't look like sine or cosine at all. So you just kind of have to memorize the two shapes. Anyway, let's do our first example. So graph 3 cotangent of pi over 2x from negative 3 to 3. So looking at this, I can see what the amplitude is. I notice that my amplitude is equal to 3. So this tells me that this is 3 up here, negative 3 down there. All right, and now we can go ahead and we can solve the inside part. So I know that this is between 0, x, pi over 2x, pi, not 2 pi, just pi, and we go ahead and solve it. And I need to give myself some room, actually. My bad. Move that over there. So what you're going to do is you multiply by the reciprocal. So 2 over pi, 2 over pi, 2 over pi. And so doing the math, that 2 over pi times 0 is just 0. The pi over 2 and 2 over pi cancel each other out. And then pi times 2 over pi, the pi's cancel. And you're left with just 2. So from looking at this, we can see that the period is just 2 minus 0, which is 2. You don't really have to say 2 minus 0, but if the two numbers here weren't really easy, like if this is an ugly number and the left is also an ugly number, you find the period by subtracting. Anyway, so that's 2, and then we have the quarter. And the quarter is going to be 1/4 times 2, which is 1/2. That means that in this graph, it'll be probably easiest if we make each tick mark the quarter, or in this case, 1/2. So I have 0.5, 1, 1.5, 2, 2.5, 3, 3.5, negative 0.5, negative 1, negative 1.5, negative 2, negative 2.5, negative 3. All right, and now this is cotangent. So if I remember the box for cotangent, this is going to go between 0 and 2. So I'm kind of imagining the box that I had earlier. So if that's my box, between negative 3 and 3 for the y-axis, between 0 and 2 for the x-axis, I can graph the asymptotes. Going back up to cotangent, the asymptotes are on the left and the right side. So I know I'm going to have an asymptote there. Know I'm going to have an asymptote there. And then I can just graph the equation. So it's 3 dots. And we graph it. And so that is one cycle for cotangent. So I can continue this pattern. Notice that I can keep on drawing this box. I can draw another box over here. And I can do it again. Oh. Of course, if you make your other box, actually make it to where it's, the same size. Don't pull a Gilbert. My bad. The box would go up to here. Wah, wah. Oh, I used purple for the asymptote. And so there's that. And then I can graph the same kind of picture. And I can repeat the process yet again. So here it doesn't make it all the way to the fourth one. Okay, but I can still create this graph. So here, here, and here. Here, here. This would be over here. All right, so technically they said only up to negative 3 and 3, so you don't have to graph this left side or this side over here. But since I had room for it, I went ahead and graphed the whole thing. But anyway, there you go. That's your graph of 3 cotangent pi over 2x. So that's an easy example. Let's move on. So this one's a little bit harder. Graph one cycle of, and then they give you the equation. And notice here I provided the box for you because it's a little more complicated. So let's see. Our first thing we're going to do is we want to rewrite this equation. So we would have negative y is equal to negative 2 tangent negative, instead of x over 2, I'm going to say 1/2 x. Make this smaller so I can have room. Okay, and then the plus 3 at the end. All right, so all I did was, in this equation, there was two parts. There was this part, and then there was that part. And so I just changed the order. Instead of the 3 going first, I just changed it to where the negative 2 tangent part goes first. All right. Next, I noticed that it leads with a negative. So we want to use even or odd properties. But tangent is odd. So before I do that, I need to do one little trick first, or else I'm going to get an incorrect answer. So I want to factor the negative out of the inside first. And I end up with 1/2 x plus, let me make it a different color, 1/2 x plus pi over 8 plus 3. So in order for you to use your even or odd properties, the negative has to be multiplied to everything on the inside, which means that you have to factor the negative out. So now that the negative has been factored, now I can use the even or odd properties, and that means the negative can go to the outside. There's still the negative out here, but that negative means I can have negative tangent 1/2 x plus pi over 8. And then you have a negative times a negative. So I did this in a lot of steps. Oh, I forgot to use the little cursor. Yeah. Struggling. There we go. But your final answer that you get from this is the negative times a negative gives a positive. So y equals 2 tangent 1/2 x plus pi over 8 plus 3. So anyway, that's our equation. Now that we have that, we can start to analyze it. So notice that it goes up 3. So that means that this is 3 in the middle. And this is going to be the amplitude plus 3. Amplitude is equal to 3. But we're going to get this and we're going to go, sorry, the amplitude's not 3, the amplitude is 2. I'm just screwing up all over the place. So my amplitude is 2, but the shift is 3. So that means that where the graph was going from negative 2 to 2, usually, you're going to go up 3 in each case. And so that gives us 1 to 5. And so that's why this is going to be a 1 and this is going to be a 5 up here, where 3 is in the middle. So the shift up is always just sits there in the middle. And the amplitude, you go up whatever the amplitude is, so 3 plus 2, and then minus 2 to get the upper and lower bound. Anyway, so that's that. Now let's go ahead and find the left and right bounds. So to do that, we get the inside. And so 0 is less than or equal to. The inside is 1/2 x plus pi over 8. So I have 1/2 x plus pi over 8. And I'm just going to go ahead and solve it. I start by subtracting pi over 8. And that gives me negative pi over 8, 1/2 x. And then here we have pi minus pi over 8. Now, think of it as a number. This is just like saying 1 and 1/8. So if you go to your calculator, 1 minus 1/8, 7/8. But you can do math 1, 7/8. So that means that this is 7 pi over 8. Okay, don't rely, especially when pi is in the equation, don't use decimals, or else you're not going to get a really good graph. You want your graph to be in terms of pi, not some weird decimals. Anyway, let me erase this so I can give myself more room. All right, and then the last step is we're going to multiply everything by 2. So if I do 2 times 2 times 2, you get negative pi over 4 x, and then 7 pi over 4. Now if I look at my period, notice here the two numbers are nasty. So it's 7 pi over 4 minus negative pi over 4. That's just 8 pi over 4, which is 2 pi. So I have a period of 2 pi. And my size of each quarter is just 1/4 times 2 pi, which is pi over 2. All right. So I can look at my sides here. I can see I have negative pi over 4, 7 pi over 4. That's what goes here and here. All right, and I know that each quarter is pi over 2. So to get to the next important tick mark, I'm going to basically add pi over 2. And if I do that, again, if you really want to, you can use your calculator. And you can say 1/4, negative 1/4 plus 1/2. Just ignore the pi's and write the pi in later. And that's just 1/4. So that means that this is going to be pi over 4. I add another pi over 2. And that's going to be 3 pi over 4. I add another pi over 2. And that's going to be 5 pi over 4. And then you have 7 pi over 4. All right. So now I can graph in my box what it would look like. So this trig function, notice that it's a positive tangent because we're using the new equation that I graphed. Or not the new, we're using the one I boxed right above this, right above here. And it's positive. And that's what our graph's going to look like. All right, so let's put this in context and graph the whole thing. Going down to my graph, I have from 1 to 5. So first let's create labels. I have negative pi over 4. Use the black marker. Pi over 4. All right, so what was different here is notice that these are just one tick mark away. But because the way the graph is, I can't do that. 0, this middle point is 0. So I have negative pi over 4, pi over 4. These are separated by 2. That means that I need to keep all things equal. So that means that my 3 pi over 4 is going to be here. 5 pi over 4 is going to be here. And here is 7 pi over 4. Do the same thing, basically go over 2. And so now there's my axis there. And so the box I'm creating goes from 1 to 5. Okay. So 1 to 5. And it goes from negative pi over 4 all the way to 7 pi over 4. So because I'm not going that each tick mark is a different number, it's like an elongated box. But anyway, I'm just going to recreate the picture I have up here, and I'm going to recreate it out here. So I have that 3 pi over 4 is the asymptote. And I have this here, so I know that the graph has a parabola, goes upward. And then I got this part right here, this dot right here. There you go. Now I can recreate the box. I can just move over. So if I create another box, I can keep on doing what I'm doing. I know that this would go downwards like this. Negative 5 pi over 4 would be the next asymptote. And then I don't have enough room for the rest, but the graph would continue. All right, so there you go. There's my quick sketch. The most important point is being able to create your box in the appropriate spot. What was a little weird is because 0 landed right in the middle. And it doesn't always happen, but because 0 was right in the middle, that forced us to change our tick marks. 0 has to be a tick mark. So instead of going that each tick mark was pi over 2, instead I was forced to make each tick mark be pi over 4. Pi over 4, pi over 4. And so I split it up into 8 pieces instead of 4 pieces. Anyway, that's that graph. So what I want you to do, oh, not yet. So let's kind of go through and fill in all the things we've observed. So if a and b are positive and c and k are any real number, then the graphs of a tangent bx plus c plus k and a cotangent bx plus c plus k will have the following. So there's really easy stuff that we know. The vertical shift, my apologies. The vertical shift will be up k, or plus k. The range of these guys is negative infinity to infinity. If you look at all the examples that we did above, the range is everything. It's the domain that's kind of weird. So I'm going to get to that in a bit. The horizontal shift is negative c over b, just like it was for tangent and cotangent. I am so sorry. I have to lock my screen because that's annoying. All right. Negative c over b. The period is pi over b. And the length of the quarter is just 1/4 times the period. All right. The domain, it changes for tangent and cotangent, but let's see. So we got a different one for tangent, a different one for cotangent, and I could put fancy equations, but really all you do for these is create your box. Okay? And all you got to do is you pick your first horizontal asymptote, and then you just add k pi. That's it. Not k pi. I lied to you. K times the period. So again, the first asymptote, the reason why I wrote it like this is because I can use the same equation for both of them. But for tangent and cotangent, the asymptotes appear in different places, just like we had up here. For the cotangent, the asymptotes start on the edges, and for tangent, the asymptote's in the middle. But once you figure out where the asymptote is, you just add a period and just keep on moving by the period over and over again. We don't really want to write the fancy formula here just because it looks nasty and it makes you think that you have to memorize it, and you really don't. All right. So anyway, just real quick, if you wanted to prove the horizontal shift and the period, you can. So if I subtract c, I have negative c bx plus c pi minus c, and then I can divide by, oops, forgot to erase there. Then I can divide by b. And notice that gives us the horizontal shift. The graph went from 0 to negative c over b. So that's the horizontal shift. Now the period is just getting the two sides, and so that canceled out, and subtracting them. So for the period, it's pi minus c over b, and then minus negative c over b. And so that's pi minus c plus c over b, which is just pi over b. So that's the proof if you wanted to get it. But if you have your tangent and cotangent, once you know what b is, the number in front of x, you can just find the period by saying pi over b. So anyway, what I want you to do is work on these next two examples. So number 3 and exercise number 4. And I want to see what you get, or just see what you get. And then I'm going to post a video to Canvas, and we'll check it out. You can check it out to see if you're right or not. Anyway, let's go to secant and cosecant. All right. So remember that secant is 1 over cosine, whereas cosecant is 1 over sine. So these graphs are a little funky. So what we're going to do is, again, it's the same thing as before. That never changes. You solve the inside, just like before. Okay? But instead, what we're going to do is we're going to grab, and also you find the quarter. To figure out what the tick marks are. So what they want you to do is secant is related to 1 over cosine. So what I'm going to do is I'm going to graph cosine as a dashed line. What does cosine look like? Remember that cosine is just doop, 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 doop. And we're going to graph it as a dashed line. A dashed line because it's not really part of the graph, but it's going to help us create our graph. Okay? We're going to draw a vertical asymptote. At each x-intercept. And we're going to draw a parabola-esque. It's not an actual parabola, but think of it as like a fat parabola at each peak or valley. So that means that we're going to graph a vertical asymptote is going to appear at each x-intercept. Because notice secant is 1 over cosine. Whenever this guy equals 0, then that means that you can't do that. You can't divide by 0. So that's why whenever it's equal to 0, you have to put a vertical asymptote. Okay. Now at each peak or valley, we're going to draw a parabola shape. So here in the middle, notice there's a valley. I'm going to kind of draw a fat parabola. On the other side, kind of the same thing. Now the parabola would keep on going, but in terms of my box stopped. So, and there you go. The actual graph for secant is the red lines. But notice how we use the cosine to help us out. So that's secant. Cosecant, same idea, except instead of cosine, it's sine. But same idea. We're going to draw the vertical asymptote. I'm just going to abbreviate it at each x-intercept. Draw a parabola S shape at each peak or valley. So in this case, my graph is going to be sine. So if we remember, sine looked like this. Okay, oh, forgot to turn the touch off. And so I have, in this case, I have 3 x-intercepts. And we can see that I have a peak or valley. So on the peak, I drew that ugly. Still drew it ugly. There you go. And that is cosecant. Now when you actually graph it, remember that all of the dotted lines aren't there. All you see is just a bunch of parabolas going up and parabolas going down. Anyway, so hopefully that's not too bad. It all depends on just graphing, knowing which is which. Secant's related to cosine, cosecant's related to sine. So let's look at this first example. Graph one complete cycle of 4 cosecant pi over 2x. So 4 cosecant of pi over 2x, I know that my amplitude is 4. So this is going to be 4, negative 4. And, one thing I forgot to mention is when you're dealing with these two, notice that we're back to 2 pi. So the only ones that have special periods are tangent and cotangent. Anyway, so I know that this is 0 less than or equal to pi over 2x less than or equal to 2 pi. I can multiply by 2. So if I multiply by 2 times 2 times 2, I get 0 less than or equal to, 2 over pi. Yeah. My bad. So if I do that, I get 0, the pi over 2 and 2 over pi cancel. And then here the pi's cancel, 2 times 2 is 4. So here my period is 4. Excuse me. And each quarter is just a fourth of that. So a fourth of times 4 is 1. So each tick mark, if I want to make an accurate graph, each tick mark should be 1. That's pretty nice. All right, and let's create our shape. So if we're looking at the box, this is cosecant. Cosecant is the one on the right. And so the box goes from 0 to 4. Remember, we're using this here. So our box goes from 0 to 4, from negative 4 to 4. All right. Now in that, what I'm going to do is I'm going to graph as a dotted line. This is sine. So I'm going to graph sine as a dotted points, and we can create our graph. So everywhere there's x-intercepts, that's a vertical asymptote. So notice that it's every 2 tick marks we're going to get a vertical asymptote. And Then for the peak, I do that. For the valley, same thing. And so that's the actual graph. So that's one cycle. And really that's all the question asks, but you know, Gilbert's a little OCD, so might as well carry it through. Every 2 pi, or every 2 tick marks is an asymptote. And I can continue the sine cycle. And I can create my graph. So I know that this point here, it's going to go down. Oop. This point here, it's going to go up. This point here, it's going to go down. And then this point here, it's going to go up. There we go. So again, all they really wanted from us was one cycle, but I went ahead and just filled up the whole graph. All right, so that is cosecant. Let's do an example for secant. So identify the period, range, vertical, horizontal transitions for, then this one, notice this one's a little bit harder, and I want to find a bunch of information about it. So let's go ahead and do it. All right, so our first task is just to rewrite it. So this is just y equals 1/2 secant x over 3 minus pi over 6, and then plus 2 at the end. All right, so I noticed that 2 is my transition, so this is going to go in the middle, and I'm going up 1/2 minus 1/2. So this becomes 2.5 up here. This becomes 1.5 down here. So it's a very narrow graph. All right. Now the inside, I'm going to put between 0 and 2 pi. Again, the inside is just this part, that part. So I add pi over 6 to each side. And then 2 pi plus pi over 6. On your calculator, if you don't want to do the mental math, that's just 2 plus 1/6. And you can stick the pi's in later. And so that's 13 over 6. And then our next step is just to multiply it by 3. So if I multiply it by 3 times 3, why does it keep doing that? Oh. Okay. What happened? What happened? There we go. I got scared for a minute. I thought I lost everything. So times 3 times 3. So this gives us, I think I'm hitting the keyboard by accident and it's zooming everything out. Pi over 2 less than or equal to x less than or equal to 13 pi over 2. And there you go. So if I'm looking at this, my period is just 13 pi over 2 minus pi over 2. That's 12 pi over 2, which is 6 pi. So this is a huge period. It goes through 6 pi, which means the length of each quarter is just going to be 1/4 times 6 pi, which is 3 pi over 2. All right, so let's kind of fill in a bunch of stuff in this table since we're already doing it. So I know that my vertical shift is up 2. Okay, my horizontal shift is, remember the horizontal shift is the number that you get on the left, and that's just pi over 2. My period is 6 pi. The length of the quarter is 3 pi over 2. And now let's figure everything else out. I'm going to save the domain and range until we actually create our sketch. All right, so if this is pi over 2 over here, and this is 13 pi over 2, remember these are the edges of, let me move stuff around. Okay, so that's where that comes from. And then each tick mark is going to be 3 pi over 2. So 3 pi over 2 puts us at 2 pi. And you can use, again, you can use your calculator. 3 pi over 2 is just 1.5 pi. Okay, so I can have 1/2 plus 1.5 is 2. So this is 2 pi plus 1.5. 3.5, you can math frac that. 7 pi over 2. Okay, and then plus 1.5, 5. There we go. And yeah, so now I'm going to create, this is secant. So secant is related to cosine. Cosine looks like this. And we can see that there is an x-intercept right here. So that becomes a vertical asymptote. X-intercept becomes a vertical asymptote. And so our graph is going to look like this. All right. So let's go ahead and graph this. Brain fart. So we're going between 1.5 and 2.5, from pi over 2 to 13 pi over 2. So for this graph, it's kind of weird. If you start at pi, or if we start at pi over 2, okay, then remember that 0 is in the middle, which means this has to be minus pi over 2. And so you're forcing yourself to say that each tick mark is pi over 2. So that means that this must be pi, which means that this must be 2 pi, which means that this must be 3 pi. And what do you notice happens? We run out of room. Okay, so sometimes that happens. If you go by the default length here, because 0 is not in this graph, but because pi over 2 would be your first tick mark, that's already too big of a step, and you run out of room. So in order to do this correctly, I'm going to adjust it a little. And so to make room, I'm going to make each tick mark be 1 pi. So I'm just kind of adjusting on the fly. This is pi, 2 pi, 3 pi, 4 pi. Why did I write 45? I don't know. 5 pi, 6 pi. Negative pi, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi, negative 6 pi. All right, so my box is going to look a little different. It's between 1.5 and 2.5 vertically, and pi over 2 and 13 pi over 2 horizontally. So 1.5 to 2.5. And then from pi over 2, which remember pi over 2 would be right in the middle, and then 13 pi over 2. Remember 13 over 2 is 6.5. Ugh, hard to draw a straight line at a distance like this. I gave it my best shot. No, that's ugly. Anyway, so that is my box. And so in my box, we have the graph starts here. Notice that the very middle point we had a vertical asymptote at 2 pi and 5 pi. So let's go ahead and graph those. 2 pi and 5 pi. And it kind of helps me graph everything else. So 3 pi over 2 is about 1.5. So every 1.5 is a tick mark here. 1.5, 1.5, 1.5. So my cosine, it's a very shallow cosine, but that's what it looks like. And then we can make another box. And so it is 6 pi long. So it's going to go to, you know what? I don't even need it. Don't even need it. Whatever. I'm going to move over 1.5, 1.5, 1.5, 1.5, and I'm going to go 1.5. And that puts me right here. And that's my sine, my cosine wave. Okay, so each x-intercept would be a vertical asymptote. Another one here. Another one here. I put that dot in a bad spot. Should have been right here. Anyway, so now let's graph it. So each peak is an upward parabola. Each valley is a downward parabola. So in this example, this is the hardest that they're going to get. If they make you do a shifted secant or cosecant, they're just nastier by default. And there you go. All right. Now looking at this, what is the range? Notice the range is everything up to 1.5. So it's negative infinity up to 1.5. And then it starts again at 2.5. And it goes off to infinity. Now the domain, all you got to do is pick your first vertical asymptote, which I'm going to say is 2 pi. And then it's just, notice that if I look at this graph, I don't know why I put green, but each asymptote is 3 pi away. There's an asymptote at 2 pi and an asymptote at 5 pi. The difference between them is 3 pi. So it's going to be plus 3 pi. Okay. Oh, x cannot be. That's the whole point, right? X cannot be 2 pi plus 3 pi k. Ugh. Anyway, so that's it for this lecture. What I want you to do is try the next one on your own and see what you get. So the next one, problem just like the one I did up here. So it's the whole shebang. Give it a shot and let me know how you do. Hopefully I'll post a video on Canvas. And yeah, y'all have a good day. I think this is the ugliest section for chapter 4. So if you can get this section down, then you should be all set. All right, y'all have a good one.